Good morning, everybody. Welcome, and it's lovely to see some new faces as well as some very old faces as well over the years.
I think the term's familiar.
Oh, familiar. Sorry, Steve. Yes, familiar faces. So, just going to start really. Take some time to have a look at those. Wonderful. It's sort of the image of the perfect road, thing that everybody wants to drive on. Lovely, smooth surface. Might not be the correct surface for what we're talking about today. Lovely, clean, white lines, quiet, sort of thing you'd like drive your convertible there with the hood down, with the wind rushing through your hair, or not, as the case may be. In certain instances, that's what we'd like to see. This is what we like our highways and our roads to be like. Unfortunately, so often is the case, and obviously just say that these pictures aren't related to the first set of pictures, or anybody that's constructed those roads that might be in here today. This is an all too familiar picture of what the public get and what we get when we're driving around on our roads. So where is the failure? Could it be poor workmanship? Potentially, maybe. Cost could be a driver of that. Could it be the quality of the pavement materials? Well, there is a chance of that, but again, standards are right up now, so there's a bit of a chance, but possibly not. Damage to the surface. It could, in some instance there is damage to the surface, maybe accidents or something's been dropped on it or other factors. But taking those into consideration, we could be forgiven, as it says there, to thinking that all problems start from the top. Very, very appropriate nowadays. We think that those things happen. There is one place that the failure is most likely to start, and I'm reminded of the chorus of a very well-known song as to where it might be, and I wonder if anyone can think about it. Anyone think about what possibly the song could be where we're thinking about? No? Okay, here goes. It's all about the bass, no trouble. It's all about the bass, that trouble. It's all about bass.
You're going to carry on?
No, all right, okay. Anyway, we talked a lot about this, and he said he was going to interrupt me a little bit earlier, so I apologise for that. At least you'll remember now. You'll remember now where we're talking about. So the problem is likely to be in the ground. So what's the solution? But why is the problem in the ground? Let's think about that first. So why do our subgrades fail? We have some very plastic soils here in the UK. We had some really wet weather, and now, obviously, what's happened over the summer, we have some very, very dry weather. So all of these things can lead to changes in the subgrade, which can lead to problems further up through the pavement layers and up to the surface. So what is the solution? Soil treatment is part of the solution. Well, you could dig it all out. Could dig it all down to a very low depth and replace it with stone. But soil treatment is definitely part of the solution. Okay, improving your subgrades so that what you're putting on top of it is going to stay where it's supposed to be, and it's going to survive. But the history of soil stabilisation is definitely not new. It really isn't a new process. Okay, if you go back 6,500, 6,500 BC, 3,000 BC in the Egyptians. And again, the question, what have the Romans ever done for us? Well, they used lime in road construction. Ermine Street, Watling Street, still evidence today of lime stabilisation being used when the Romans came over here and realised that we do have those wet plastic soils, and it's very difficult to get anywhere. So I'm going to hand over now to Steve for a bit, who's going to start talking some technical stuff to you, and he's going to not sing, and he's not going to dance, and he's not going to do anything like that. So, he didn't tell me he was going to.
No promises on that front, but unlikely. Just a little bit of theory. I know some of you may have heard this before, but I took a look a bit at the theory of soil treatment, and for all of the cement producers in the room, I'm actually going to talk a little bit about lime as well, because it has some very great added benefits. Next. This was referred to earlier in terms of BSEN 16907 Part 4. I was part of the drafting committee on this, which is the European standard for treatment of soil with binders. And there's a difference between soil improvement and soil stabilisation. Soil improvement being an operation which modifies the physical properties of material, such as the water content, plasticity, water and frost susceptibility by the addition of a binder. And really the only difference between soil modification and soil stabilisation is that with soil stabilisation you have guaranteed that the material changes the same characteristics in a way that renders it stable, in particular with the actions of water and frost. So soil modification can be a short-term, medium change, where stabilisation is a locked-in change to the properties of that soil. What does lime do when you add it to soil? It's not just, when you're just adding lime, it's not just drying it out. A lot of people say, oh, we've got a wet site, can you come and add some lime to dry it out? It's seen in a lot of cases as a short-term fix, soil modification and treatment, but no. There's a cation exchange with the addition of negatively charged calcium cations onto the surface of the clay particles. That causes electrostatic disturbance induced by that, which means that clay particles are now attracted to each other, which causes the soil to flocculate. And what that looks like, rather than as a science lesson, is effectively you're going from a nice mouldable clay at the bottom, which is nice and wet. That exchange causes a flocculated clay. It acts slightly more granular in nature. And part of that physical change with the lime is that if you were to add a cement or other hydraulic binder to that, it's very difficult for it to mix in. Once you've flocculated that material, it is then very readily acceptable to cements and other binders to get a very high strength addition. Lime, it doesn't purely just dry the soil out. Effectively, geotechnically, lime changes the soil. It increases the plastic limit of the soil. So therefore you may have a soil, at the start, the same soil, it's sat here. This is taken from Earthworks, a guide from Paul Novak and Peter Gilbert, the ICE update in terms of that one. So your natural soil sits here, you're in the plastic state. So your soil is wet of plastic, add lime to the soil, plastic limit increases. So the same soil after the addition of lime, that soil was then in the solid state, much more resistant to change, easier to compact, easier to handle, easier to traffic, and gives you a better product. It also, addition of lime, it reduces your maximum dry density of the soil, easier to compact, and lower or increases your optimum moisture content. So therefore your soil is more likely to be, it increases the again ability to use that material once it's been limed, is more likely to accept it within an embankment. We do have, within the use of soil treatment working back up, we do have some very nice standards, and this is from, we'll split it between the standardisation bodies, looking at the moment what's within the BSI. We have the top BSI 16907 Part 4 referred to earlier and referred to from National Highways. And to follow on from the National Highways talk earlier, the 5-year review of 1907 Part 4 kicks off in December 2023. So Paul, that will line up with the session. And one thing that has been talked about from the member countries within that is looking at increasing the range potentially of binders within 16907 Part 4. So that is being looked at in terms of slightly widening the scope. Because at the moment there's purely standardised binders within it, but also what standardised binders are included it hasn't been voted on, but the chances are it will be reviewed following 2023. Within the pavement, 14227, various parts refer to hydraulically powered mixtures, which are in your pavement foundations. 9227, relatively new, has produced hydraulically bound materials, the production and installation in the pavement, a guide of how you produce and install those materials. And backing that up is testing. You always say you can build the greatest job in the world, unless you can prove it, it's worth nothing. So 1924 parts 1 and 2, it talks about the sample preparation before and during treatment to prove that you're doing your soil treatment works properly. We have here DOT spec, as referred to earlier. CD225, the design of pavement foundations, includes 4 stabilised subbases within it. Series 600 earthworks, although it's under review, at the moment is limited to capping. Series 600 has no earthworks treatment included within it. Within reference documents, Series 800, which has the unbound cement and hydraulically bound mixture within it. So at the moment, which is being addressed, I believe, within series, well, it won't be Series 600, it's going to be CC201, will hopefully look at soil treatment within general earthworks. And Al, to give you to give me a breather.
There you go. Yeah, obviously we can't move on to the other part of the presentation without actually putting the BritPave hat on again. Just to let you know that we have, since 2004, when we formed the Soil Stabilisation Task Group, over the years we have worked alongside, as they were, Highways Agency, then Highways England, now National Highways, along with other bodies as well, to produce a number of guidance documents covering soil stabilisation in its many forms, improvements in sulphate-bearing soils, hard standings, roads, and also to the point now where we have the definitive guide to soil stabilisation, which we worked alongside National Highways quite closely to produce a document that was going to offer something alongside the HA 7407, which is now obviously not going to be updated and sort of disappearing into the distance. So please go to visit britpave.org.uk, get onto the soil stabilisation site, and you can have these as downloads. You can order hard copies. There are a few of them still left.
All free of charge, I hasten to add.
They are all free of charge, but obviously with carbon reduction, it might be worth just downloading one and keeping it on your laptops. So back to you, Steve.
As the theme for today is obviously the 100-year road, I decided I would talk about the 120-year railway instead. Which we're all familiar. Apparently there's a big railway line being built between London and Birmingham, and it may go to Manchester, depending on the cost of the bit it takes to get to Crewe. HS2 in there, and having spoken with some of the lead designers, that one, have actually put a very high specification on the earthworks. Because, as Al said, unless you start from the base up and anything you build, you wind up putting, as we would call it proverbial, very nice skin on a rice pudding, which whatever you do to it, it's going to crack. So what they have done on HS2 is actually introduce 3 additional clauses based on the Series 600, 648, 49 and 50, which is using the stabilisation of using lime or lime and cement to form the high-speed rail earthworks materials. And also 650 using other combinations of binders. If you can prove it works, it hasn't ruled out other binders. So it's not purely limited to straight lime and cement. Very high, one of the hardest specifications for earthworks for infrastructure in the UK. We have come across similar specifications under high bay warehouses for the likes of Tesco's, where they definitely don't want it to move. But in terms of infrastructure, one of the highest specifications, have a lower embankment fill, where you have to achieve greater than 95% MDD with less than 5% air voids on a 4.5k rammer, and the upper embankment fill, which is the top 5 metres of the fill. It's not just a 1 or 2 metre on top. So the top 5 metres of your embankment or below treatment is greater than 98% density on a 4.5k rammer, below 5% air voids, and an EV2, a stiffness of greater than 60 MPa. It's one of the toughest specs we've achieved, and Steve, if you don't mind saying, it's actually proved quite tricky to achieve that without significant additions of water and other materials in some of the materials we have within the UK. But once it's down and complete, and from our experience on C1, which is the contract at Maple Cross, once it's in and to spec to the not HS2 spec, I need to say the HA spec, the HS2 spec, it's bulletproof. It's not going anywhere. And so then work through. But coming back to our 100-year road, recent examples of using stabilised soils on highways is within the North Norwich Distributor Road, where Class 2 and 3 foundation was installed there. Steve was heavily involved with that as well. And working with Norwich Council, interesting to compare to the Belgian experience there, the decision was made, rather than going for the design was for a thinner, high-strength layer, we actually went for a thicker, slightly lower strength material, and that's been in now 4 or 5 years. So 4 or 5 years, and no issues. So in terms of treating the natural soils. Newark to Ridmapool, similar timescale, a HBM layer using imported planings and some Site 1 materials, and a guided busway was a full Class 3 foundation was put in to remove any imported stone. So stabilised soils within highways, some recent examples, but from my view, working on the earthworks upwards, it definitely works. So just going to have a look here in terms of a treated soil, in terms of long-term benefits. This is an example from a European conference from 2019 of a road that's built in Germany in 1979. They took samples in 1990 and 2013 to look at carbonisation, or carbonation, so then compressive strength. It was initially treated to the German specification, which was 2.5% lime addition, 98.7% relative compaction. I think they had to achieve 98, and below 12% air voids. A lot of granular, more granular-ish soils in Germany, so tend to have a higher air voids allowance than we would normally allow within the UK. Very simply, it's treated with lime. In 1990, they were getting average compressive strengths of 1.3 to 3.4 MPa. That was going up to some places 6.1 of 2013. So it is still increasing in strength over time with the addition of binders, and with a notable increase in the upper layers. I'm going to talk a little bit here about carbonation. Soil stabilisation can get a bit of a bad reputation in terms of the amount of carbon embedded into it. But carbonation rate is the percentage of CO2 that's captured during the application compared to the CO2 created in the manufacturing process. And what this German study found, that over the period of time, there's 40% carbonation. So 40% of the CO2 that was produced in the manufacture has been captured during the life of that product. So it is taking back CO2 within. So the use of a lime or cement or other materials within it, it doesn't automatically. It's the carbon is there. It is actually going to get some of that carbon back. Quick one, carbonisation. The lifestyle, the lime actually has a natural sink. What we call the circle for lime starts off as calcium carbonate. Heated a lot, turns to calcium oxide. So hydrated or milk of lime comes through. Water then comes back into it, turns back to CO, turns back to calcium carbonate. Increases the strength, sorts the soil out, and sucks in CO2. So it actually is from a European Lime Association publication. So lime can actually act as a natural sink. One of the interesting things is from comparing within the national highways, was a thought of us taking the 2020 carbon usage and that. Not a lot of stabilised soils and embankments were used in 2020. But a stabilised soil can give a longer duration in terms of life. So you may use more carbon compared to 2020. If you were to go and design an embankment with a lot of lime and cement in it, your carbon will probably increase from that baseline. But I would definitely state your design life will increase. So in terms of whole life costing, I would suggest it probably comes down. But on this basis, soil stabilisation has a carbonisation rate of 30 to 40%. It puts it back in. And going forward, others will talk about this later, binder producers, both lime and cement, are working towards carbon zero in terms of production of that material. So lime itself is a natural carbon sink as it reacts. So soil stabilisation, carbonation, 35%. So over time, the use of lime and other materials will actually be carbon negative because of the nature of the process. So if they can produce the carbon, produce them with binders with zero carbon. With carbonation, it becomes a carbon negative product in terms of using soil stabilisation. And finally, we've mentioned about climate change. We are facing more flooding, higher temperatures, this, that and the other. A stabilised soil is more resistant to water erosion from flooding and can be used for water retaining structures. ICOLD, which is the International Committee on Large Dams, about 4 or 5 years ago, have now started to accept you can build cohesive dams with lime addition in terms of longer term and erosion resistance. A stabilised soil is more resistant to frost damage, although we're actually getting more frost, we do get sufficient, and more resistant to drought conditions. And a stabilised soil is durable, so therefore we think in the long term, a stabilised soil and soil treatment for your earthworks and lower pavement layers will increase the design life and the construction life of machines. And will that be it? Any questions? Or do you want us to sing it?
You can sing it, didn't you?